All right, today we're going to talk about exponential and logarithmic functions. Only thing we're going to talk about today is graphing them. We're going to split this into two. We'll only talk about exponential today. You'll need a graphing calculator on these, so go ahead and get yours ready, and we'll begin on these. So what we need to understand about exponential functions are functions that have a variable in the exponent. So there are numerous families, infinite number of families for that matter, that are exponential functions. This is the 2 base function. We have 2 as a base value, and then we have a variable in the exponent. The fact that we have an exponent is not what makes a function exponential. Like this quadratic function does have an exponent, but the variable is not in the exponent. So if there is no variable in the exponent, it is not an exponential function. This is our doubling family. This is our tripling family. This is our quadrupling family, and you get the idea as we move through these things. So again, we're just going to take a look at our exponential. You notice the logarithms are written on the right there, but the logarithms we'll talk about tomorrow. So on our exponential function, what we have here is just plugging in the values. So a couple of things we want to remember. Remember, when we have a negative exponent, that is not the same thing as multiplying times a negative. What that means is the numbers that are in the numerator should be in the denominator, and the numbers in the denominator should be moved to the numerator. So I'm going to go ahead and plug in our first value. See, we have plugging in a -2 here, and we're plugging in -2 as an exponent to 2 to the -2 power. What this is saying is 1 over 2 squared, or 1/4. Now, I've taken these to my calculator. Hopefully you've got yours ready by now. And on this calculator, I've got these values put in already. So we're just going to graph these points as we see them. You see -3 is also in the graph there. -3 is like 1.125 right down there. -2 is at a quarter. -1 is at a half. So we barely can even see these moving. And then here's a point that I want everybody to highlight. That is 0, 1. That is kind of like on a quadratic, the origin. On a quadratic function, we always go through the origin. Well, on an exponential function, we always go through the value 0, 1. If we're not going through the value 0, 1, what that means is the function has been transformed. So we're going to graph a spot at 0, 1 there. Next thing we see is at 1, 2. And again, if you think about that, 2 to the 1 power, of course, is 2. And now we're going to start seeing that exponential growth. 2 squared is the 4th power, and then 3 is at 8. So 5, 6, 7, 5, 6, 7, 8. So we're there. So this is what our exponential function is going to look like. I'm going to zoom in real quick, because what we have happening is what's called an asymptote. It's going to run right through this line right there. And then now we start seeing that exponential growth, because at the beginning we are dealing with such small numbers that we're barely seeing any change happening there. But once we start getting to these integers, we see that the function starts flying. So this is what our exponential function, the doubling family, looks like. Go ahead and put these ordered pairs over here. 0.125, and again, resist the temptation to come in here and start putting in negative numbers. Those are not negative numbers. And then we will come back and look at the log base 2 is what that's called, but the log base 2 is the inverse function to this function. I want to talk about a couple of things while we're here. That is the domain and the range. The domain of this function is how far left and right that it's going. Well, we can see that it's going infinitely left, so it has a boundary of -infinity, and it's going actually infinitely right. So our domain is all real numbers. This is another spoiler for you. On an exponential function, the domain is always going to be all real numbers, just like quadratics. So if you have that, the domain is all real numbers. Now the range, on the other hand, is where we have some issues. We see that this range value, it is rising infinitely up and down, but it's hitting a wall when we get to the x-axis. So we have a range of values that will not get lower than 0. So that's our domain and range for the exponential function 2 to the x power. That's the doubling family. Another thing we need to recognize and point out on this, since our base value was a value greater than 1, we have exponential growth. Exponential growth. Exponential growth can go in both a positive and a negative fashion. Drawing another one, that's actually considered exponential growth as well. It's just exponential growth that's growing in a negative fashion. The way I like to think about exponential growth, it's either an airplane taking off or a submarine taking its dive as we move left to right. So this blue line that I have drawn, we can clearly see that's an example of a plane taking off. And then if I had the submarine diving, that's what that would look like. That's also an example of exponential growth. And the reason why we have the exponential growth is because of the value of 2, that base value that is greater than 1. So as we look at this one, we can see that our base value is equal to 1/2. When our base value is between the number 0 and 1, in other words, a fraction, then we have what's called exponential decay. And using the same examples as before, this would be the airplane landing or the submarine submerging. Both of those are kind of the end of their trip. Think of that. It's the decay of their trip. Their trip is now coming to an end. So we'll graph this one as well. We have a base value of 1/2. I just went straight to my calculator on this, but do understand that what we're essentially saying here is 1/2 to a negative 2 power. 1/2 to a negative 2 power. So let's take a look and see that the values that we have here. We have a value of -3, 8, -3, 1, 2, 3, 4, 8. We also have a value at -2, 4. We have a value at -1, 2. And of course, we have the value at 0, 1. We just talked about that. That is where it's going to hinge. If you look at that x equal to 0, if it's not at 1, you know you have some form of a transformation. And now we're about to see what a decay looks like. So we have a 1/2 value at 1. We have a 1/4 value, a 1/8 value, and then this is just going to slowly decay, half and half and half. So this is that asymptote that we saw earlier. It's getting closer and closer to this line, but it's never actually going to touch that line because we can't divide our way into being 0. So that number is going to keep getting smaller and smaller and smaller till it's incredibly insignificant, but it's never actually going to be 0. So we have another asymptote. That's called a vertical asymptote. So that's what our family of functions look like. Just like that. And again, you can see the log base 1/2 over there. That is this function's inverse. So it's going to resemble, but it's going to be an inverse function. So we've seen exponential growth. That's when the base value is greater than 1. I put an equal sign. Actually, when it's equal to 1, then nothing's happening. But if the base value is greater than 1, it is growth. If the base value is between 0 and 1, we have decay. And we have one other family. We have infinite number of families, but they're going to fall in one of three categories. It's the one that we just showed, the growth. It's the decay. And then we've got one more. We'll take a look at it real quick. All right, and the last little function that we're going to have here is the E button on your calculator. You can see I've highlighted that right here. It's the button right to the left of 7 and 4. If you hit second and then that button, you have the E. That's Euler's number. What Euler's number is a number that calculates continuous compounding. Bacteria grow in this fashion. Bacteria don't wait for a certain time period to elapse. They are immediately, as soon as a bacteria reproduces, it is automatically a reproducing organism. This is called a continuous compound. It's continuous growth, either of those two things, and it's Euler's number. If you're curious what Euler's number is, all you need to do is take e to the 1 power, and you're going to see an irrational number. If you're curious, it's 2.73 something, something of that regards. Well, actually, we'll see it in just a second because we're plugging in those values. Now, this one is not even worth trying to plug these in by hand because it's a irrational number. Euler's number is. Let's take a look. Actually, I've got it right here. Here's what Euler's number is. It was close. 2.7183. I had my 3 and my 8 backwards there. So that's Euler's number. So what that's basically saying is he's calculated a continuous growing organism is just between doubling and tripling over time. So let's input our values here, and we're not even going to graph this one. We just want to get familiar with these numbers. But if I were to graph these, it would look like the one we did at the beginning, but it's basically between the doubling and tripling family. So here are our input values. -2 is 0.135. -1 is 0.3678. 0, of course, is 1. Even Euler's number has to follow that category. So that's actually where we'll start to look if we're trying to figure out transformations, which is where we're going to head next is transformations, how much we transform these things. One thing I want to point out, we're not doing it today, but one thing I do want to point out, ln, that's called natural log. Natural log is the inverse to Euler's number. Here's another thing I want you to point out on your calculator. Anytime you have a function on your calculator, like you see ln here, the second and that button is always the inverse of those things. Like if you look at the trig and you see sine, right above it is inverse sine. Any function that you have, the inverse is the second of that. So if you're working on your ACT, you can kind of use that as a cheat sheet. If you see a math that you're unfamiliar with, but you see the button, you can know to do the inverse of that by hitting second and then that button. All right, Euler's number is not really anything special except for that it has a specific purpose, but it's no different than the, sorry about that, it's no different than the doubling family or the tripling family. It's just specifically the number 2.7183, and that's repeated. It's like pi, it's an irrational number. But the graph is going to look similar to these two. It's just going to fall between the two. So tomorrow we'll take a look at our log-based stuff, and then we'll start transforming those things. The transformations, we've actually already studied these. We know how to move stuff left and right, up and down. We know how to stretch and compress them. It's going to be the same process with these. They just are shaped differently. All right, you've got a small assignment. Go ahead and get to work on that. Good luck. So we last talked about exponential functions. Primarily, we started talking about the x squared family. We're actually going to talk about the inverse today, which the inverse of an exponential function is a logarithmic function. The logarithmic functions, I like to attribute those to kind of what algebra 2 is, because you have all seen some form or fashion or some kind of reasoning to all the math we've done, but this one is kind of out of left field. You've never discussed, you've never seen logarithms. We will get into solving those, but now we're just going to kind of look and see what their functions look like on a graph. But what I want you to understand is a logarithm is the natural inverse of an exponential function. So just like we get rid of multiplication with division, we get rid of addition with subtraction, powers with roots, and so on and so forth, we do the same thing with logarithms in order to get rid of exponential functions that have a base. Now, just like the bases, we could have had a 2 base, 3 base, 4 base, infinite number of bases as we go down the list here. There's also an infinite number of logarithms. And it's very easy to spot these because the inverse to a base 2 is a log base 2. And the way that this looks is log, a subscript 2, and then an x value. So when we see these two put together, they are going to cancel one another out essentially and become 1. So when you log base a base of the same amount, they offset one another. Now, you're going to have a hard time finding the log base button, so let's talk about where that is. If you'll look on your calculator, again, just like yesterday, you have to have your calculator on this. You're going to hit the alpha button, and then you will hit the F2 button up there at the top, just like you're trying to get a summation sign. And if you'll look down the list, you're going to see it spelled out log base. Once you press log base, it's pretty self-explanatory. They're going to give you a space to put the subscript number, and they're going to give you a space to put your variable. So I've already done this, and you can see I've got a hidden graph here. So I'm going to remove this and see what we have underneath. So this is what our log base looks like. One thing I want to point out on a log base is how weird our numbers are. It's sometimes very hard to graph these just because it's so hard to find values. I'll give you a hint to those as we go on, and that is just to use the inverse of the exponential functions. But let's just take a look at a few of these and then we'll graph them as well. So you notice we're getting error readings at 0. Now, if I were to back this thing up, I'm going to continually get error readings as I go along. So I'm going to graph the points that I definitely know. One of these you're going to hopefully remember from yesterday, but at 0.25, we have a value of -2. That would be right there. And at 0.5, we have a value of -1. And then 0.75, we're at -0.1. And then here's a very crucial point, 1, 0. So we have a point right there. And then I'm putting a highlight on that point because just like the exponential functions went through 0, 1, logarithmic functions are going to always go through 1, 0 until they are transformed. Now I'm going to look for some other points as we go through here and just kind of highlight these. So we're going to go through the point 2, 1, puts us right here. We're going to go through the point 4, 2. And then let's just go ahead and move all the way out to 8, 3. So this function looks like this. And just like the exponential function, anytime we have inverse functions, they're always reflective across the y equals x function. So this is what this is going to look like. I'm going to highlight some points. I've got some on here specifically, and then we will see what we're talking about. So, for instance, we have the value 1, 2 from yesterday. Well, notice we have the inverse function, which is 2, 1. So we have an ordered pair 2, 1. We also have a ordered pair 8, 3. Had we looked further down our exponential functions, what we would see is that the 2 to the x power has a output value of 3, 8. Just like we were talking about, 0, 1 was a ordered pair yesterday. Today, the ordered pair is, sorry, I said that backwards. 1, 0. Today's ordered pair is 1, 0, not 0, 1. 0.5 is on my list here. You can see we have an ordered pair of 0.5, negative 1. So I'm going to put that on my table. So my hint to you on this is anytime you're asked to do a logarithm and you're comparing it to an exponential, just take the inverse ordered pair. Kind of like I'm going to just steal this one right here. We have a ordered pair of negative 2, 1.25. So I'm just going to do 1.25, negative 2. I'm not going to care too very much, to be honest with you, about the ordered pairs for a logarithm. And really the main reason is you can basically see how weird our ordered pairs are. You're always going to have decimal answers because you are dealing with irrational numbers. All right, and then here's the other thing we want to take a look at is the domain and range. We talked about that yesterday on the exponential. Remember, the domain is how left or right our function is going. Well, if you look at our green graph, it hit that wall at x equal to 0. It asymptote. That is called a vertical asymptote. We had horizontal asymptotes yesterday, or excuse me, that's a horizontal asymptote. We had the vertical one yesterday. So our domain will never be lower than 0, but we can see as it moves right, this function continues to move right. So there is no restriction to the domain moving forward. And then the range of these values. Well, I can see it's going forever down, so that would be negative infinity. And I can also see that it's going forever up, which is positive infinity. Now let's stop and take a look and see what we think about our domain and range. Now take a peek over there at the exponential domain and range. This is always going to happen. You'll see that the domain and range are also inverse. These are inverse functions, so their domains and ranges are always going to be inversed. Now, this has never been anything we've ever pointed out because all the functions we've dealt with in the past don't have restrictions. The domain and range was all real numbers. So we've never even concerned ourselves with this. But now that we're getting into some functions that have restrictions, we need to highlight this. So this is going to have a range of negative infinity to positive infinity. The domain is going to be the same thing. Just like yesterday, gave you a spoiler. The spoiler today is anytime you have a range of a logarithmic function, it's going to be all real numbers. So our ordered pairs are inverse, our domain and ranges are inverse, and then of course our functions have a reflection across the y equals x, which we can clearly see right there. So this was a function that had an exponential decay. We don't recognize logarithms as decays or growth. They just are what they are. But we're going to just jump right into the equation on this. So we'll take our equation here, and we see the correlation between the inverses. Remember negative 3, 8? Well, we have an ordered pair at 8, negative 3. We had an ordered pair at negative 2, 4. Well, there's the ordered pair 4, 2. We had the ordered pair negative 1, 2. There's the ordered pair 2, negative 1. And then the most important one, 0, 1, 1, 0. Now you notice this doesn't follow true into the other numbers because we start to get error readings. But for the most part, this is going to be what we're looking at. And again, we don't have to put all these points in, but 0.25, ordered pair of 2. So my suggestion when trying to find ordered pairs to graph a logarithm, still from the exponential, and that's what I'm going to do real quick. So my exponential, excuse me, had an ordered pair of 1/4, comma 2. So I'm going to reverse that. And there's my ordered pair. And I'm just going to steal from the whole list. We had one at 1, -2, or excuse me, 1, 1/2, so I'm going to put one at 1/2, 1. I had an ordered pair of 0, 1, so I'm going to have one of 1, 0. And then ordered pair of -1, 2, so 2, -1. And I'm actually going to graph the one that's a little further down the list. It's going to help me graph. And that was the ordered pair 8, -3. So now that I have my ordered pairs, I'm going to take this to a graph. We have an ordered pair, 1/4, 2, 1/2, 1, and then the most important one, 1, 0. Then we're at 2, -1, and then lastly we're at 8, -3. Which is here. So these functions are reflected across the y equals x. Don't worry about the fact that they're crossing each other. That has nothing to do with anything. They can do that. So once I've graphed this, now I have my logarithmic function. And you can see it is the inverse. That's that diagonal line drawn through the middle. Those are reflected of one another. And that's because they are inverse functions. Their domain and ranges are also going to be inverse functions. Again, the hardest part of the logarithms is really just finding points that work. I traded my table out over here. I set my table to count by 1/4 so that I could see more values to plot because it's really hard to find those. Again, just steal from the exponential is a good way of doing those. And the last thing we'll take a look at is the Euler's number. So we're talking about Euler's number. The natural inverse to that is natural log. That's the button ln. We don't have to hit second to do this. So here's what we have. E to the x power is inverse to ln x. And again, that is the button just to the left of the 4 and the 7. Got a nice group of ordered pairs here. You can see those. I've got my list down here. But what I'm going to do, again, is just steal from my Euler's number function. So if I had an ordered pair at -2.135, well, that means that the natural log has an ordered pair of 0.135, -2. Since this one had one at 0.3678, -1 would be an ordered pair. And this is going to go through 1, 0. Make sure you have that one in your ordered pair. 2.7183. There we have that. And then lastly, 7.3891. 2. Now, I'm not obviously going to find those on the x-axis precisely, but we're not looking for precision on these per se. Matter of fact, there is no precision because this is irrational numbers, and you cannot pinpoint an irrational number. You can only estimate an irrational number. So we have these. What we're going to do is take these to the graph and see what they look like. Nothing special to it. It's just basically a base of 2.7183. These are used pretty common. I like them. It's easier to type these in, to be honest with you. It's easier to work with these. So we do need to get familiar with them. So here we are again. We've got our graph. I'm actually just going to pause and plot these points because really all I want to do is give you a visual of what these two functions are going to look like. So I'm going to pause it. You're going to have lines just magically pop up there, but that's okay. I'm just drawing them from my graphs that you see on the right. So there we have it. This is the Euler's number graphed right next to the natural log. Again, nothing special here. They're not doing anything crazy, anything unique. It's just something I wanted you to get familiar with. I do want to point out the fact that these are reflectant across the diagonal line. Y equals x. And that's what inverse functions always do. They're the equal distance from that line. If I were to draw a straight line from any point on the graph, it's going to meet perpendicular and it's going to be the same distance. Obvious point is this one right here. We can see that those are the equal distance from those things. So that's what we have. We'll start talking about the transformation of these tomorrow. We've already kind of touched on these. We've already kind of touched on these yesterday with exponentials. Give you just a little taste of what we're going to see tomorrow when we talk about natural log base, or not natural log, but log base 2 of x. That is the parent function. Just like any old transformations we had, if we go to the back of this thing and drop a plus sign, this thing's going to get shifted up 2 units. If the action takes place inside of a parentheses, it's going to move left or right, and it's going to have an opposite effect. So this one, where it feels like we would go left to, we're actually going right to. And if we were to multiply in the front, we are going to have a stretch if it's a number greater than 1, or a compression if it's a number between 0 and 1. So that's what we'll take a look at tomorrow. We'll have the multiple transformations. Hopefully we will have a good recollection of our transformations, and could be a pretty easy lesson. You've got another small assignment you could work on. Good luck.